All right, so here we are, another question. Let me let's take a moment to get the audio, check the audio, and then I'll pop out the chat. Take a deep breath. Hello. Take a deep breath. Yeah, audio is working fine. We'll just continue on as I have been. Next question is, construct binary search tree from preorder traversal. I'm thinking if there's anything else I need to do before we begin. I could just get right into it. So yeah, here we go. This could be closed. This could be refreshed. All right, so construct binary search tree from preorder traversal. Given an array of integers preorder, which represents the preorder traversal of a BST binary search tree, construct the tree and return its root. It is guaranteed that it's always possible to find a binary search tree with the given requirements for the given test cases. A binary search tree is a binary tree where for every node, any descendant of node.left has a strictly less than node.value, and any descendant of node.right has a value strictly greater than node.value. A preorder traversal of a binary tree displays the value of the node first, then traverses node.left, then traverses node.right. Okay, example 1. Constraints, preorder.length, preorder of I is less than or equal to 1,000. All the values of preorder are unique. Acceptance rate's pretty high. Okay. So example, preorder is here. Output is, what do they want exactly? Preorder 1.3 is 1.03. Construct the tree and return its root. Binary search tree. It's guaranteed that it's always possible to find a binary search tree with the given requirements, given test cases. A binary search tree is a binary tree where for every node, any descendant of node.left has a value strictly less than node.value, and any descendant of node.right is strictly greater. Preorder traversal displays the value of the node first, then left, and then right. Okay, I think I understand. So basically, you're going to go node by node, like, element by element. And what's going to happen is if the element is smaller, right, then it's going to be the left subtree. If it's larger, then it's going to be the right subtree of that, the parent, whatever the previous parent was. So I should probably put these onto a stack. So 7 becomes the right subtree of 5, and 10 is not the right subtree, not the left subtree of 7, not the right subtree of 7, but the right subtree of 8, right? Not even 5. Pop 5 to get back to 8, and then 12 is and push 10 on there, and then 12 is going to be the right subtree of 10, and then you pop 10. So you just use a stack, I think, is the way to go. This is pretty straightforward. Yeah, I think that's the idea. So let's do that. How I do, yeah, okay. So we're going to say for each tree node result, this always has a value in it, right? Yeah, always has something. Constant x in preorder, and we're going to have a stack of ints. Actually, it's going to be tree nodes. Stack. We're going to say stack's empty. Actually, we always push onto the stack. I always push on the stack. T is going to be a new tree node of x. Push T onto x eventually, and we're going to say if T is not empty. It's really a while loop, actually. So if, how does this work? result is going to be the first tree node, by the way. Maybe make this an optional, I don't know. Okay. There's the root. Now what we're gonna do is say on the left side, right, so the next value x, push t. I don't know. Oh, excuse me. Maybe I want to do something like the following, actually. Maybe I don't want to do the whatever I was doing before. Just pop the stack. Okay. So I push this tree node onto the stack. Now, what's going to happen is the way this is going to work is the next value is either greater or less than the previous value, right? And the previous value is what's on top of the stack, always. Excuse me. It's not quite as simple as I thought it was going to be. The next node that you see, if it's larger than the previous node, it's going to be the right subtree. If it's the smaller node, it's going to be the left subtree. And either case, I think we push something onto the stack. Is that true? I think so. Excuse me. Yeah, we always push this next value onto the stack. That just always happens. All right. Yeah. Okay. So there are two possibilities, right? Stack is not empty, and st top is less than x, or stack is not empty. And well, I just do this. Just do two if statements. It's fine. Not make this so complicated. So if x, it really should be the other way around. If x is less than the top, that means it's the left subtree, which means we're going to say st top left is going to be t. Otherwise, right is going to be t. And when this case happens, we pop the stack, by the way. Is this correct? Or do we always push something on the stack or not? No, I think I'm not sure about this. It's something like this. What you end up with is the next value compared to what's on top of the stack of the previous value. If this next value is, excuse me, if it's larger, that means it's got to be on the right subtree. It's going to be a right subtree. And is it going to be the right subtree of the previous value or the value above? Well, because could just as easily be, well, actually, that's a good question. It needs to be larger than the value behind, but smaller. That's actually a really good question. I don't know. How far up do you go? Because you're going to add this to a right. So if this value is smaller than whatever's on top, then we just go to the left and keep going, right? Keep pushing. But as soon as you see a larger value, it could go directly on top of the stack, or directly where it is, right, to the right. Or you may need to go further up, because it could be larger than what's on. Yeah, it could be larger than. And I think you even pop that value. Yeah. So it's going to be. You have a whole bunch of things that need to happen. The stack is not empty, and stack.top is larger than, or x is larger than stack.top. No. So pop the stack, right? You don't actually put it there immediately. That's the thing, right? It could go to the right. That's what I'm getting at. You may have to do a lot more popping. Oh, I see. Oh no! Oh. Excuse me. All right, I'm gonna go lay down. I got confused. Managed to confuse myself in this one. It's a little more complicated than that. So the issue is that this larger value, it could be larger than what's on top of the stack. And I'm gonna pop that node, or it could be larger than the value above that. So I actually need to. There's a lot of popping and saving I need to do. That's I'm getting confused about. Excuse me. Oh, these questions are so tricky. I've noticed that they're like deliberately made to like really trip you up. Okay, so one more time. The logic is, yeah, it's kind of involved. It's always got like some caveats to them. Something tricky about it. All right, one more time. So you're going to pop, right? You're going to look and you're going to say, okay, this value is larger than the last node that I inserted into the tree. Because it's larger, it's got to be a right subtree of something. The question is, if it could be further up the tree, right? Because if I try to place it immediately, then not the parent, but the parent of the parent actually could be smaller, in which case this wouldn't be a correct binary search tree. So I need to figure out keep popping and saving the previous value until the not the parent, but the parent of the parent is larger. Yeah. Excuse me. Or until the entire stack is emptied. In which case I do need to do things a little bit differently. Yeah, that's kind of the key to this. There's like something here that's a little bit special. So we'll just do it this way. So if not result, set result equal to t. And then return result over here. Then also stack's not empty. We're gonna say, really do a while loop here. While the stack is not empty and x is less than st.top, or x is greater than st.top, I'm gonna say tree node previous. You know, I don't know. I might be able to like simplify this a little bit. And then we just do a simple while loop. Well, yeah, I mean, it's if no, just do it as I was doing it before. It's fine. So if x is less than what's on the top, we just go to the left and move on. However, if we need to put in the right side, we're going to do it this way. While it's not empty and x is less than the top part, we're going to pop st, and we're going to set previous to st top, and then pop st. And at some point, we're going to hit a point where it's either A, st is empty, or B, st top is less than the value of x, in which case we could say take st top to the right and set that to t. It's not going to be, it's actually previous right should be t. That's actually important here. Because you could pop all the way to the, you could pop all the way through the stack and end up with an empty spot. It's if this top part, we're actually going to pop first. Pop first, and then do this routine. So we take previous to be the top and then pop. And then what happens is now, this is not actually the parent that we're considering, it's actually like the grandparent, right? If the child is less than the grandparent, x, right? What we're going to insert is less than the grandparent, then we can insert it into the parent, which is like p and gp. It's not previous, but p. Let's do it that way. So we'll set the parent to the top and then pop the parent off, and now we're going to keep going, keep updating the parent and the grandparent, check the grandparent against this new node. While our stack's not empty and the grandparent exists, check that this is less than the grandparent x. If it's not less than the grandparent, actually. So while this new x value is greater than the grandparent, then we need to set the parent to the grandparent and pop the parent. And pop it off the stack, and then look at the next grandparent and keep going, right? Because we're gonna, because we're larger than the parent, we're larger than the grandparent means we have to go to the right of the grandparent, and we keep going all the way up. And then eventually we get to a parent. We either have no more grandparents to look at, or we get to a grandparent where x is less than that grandparent, in which case we can add our node there, add our node at that parent's on the right side of that parent. Yeah, that's really confusing. I think that's the solution, by the way. I think that's it. It's that simple. But it's definitely oh, I made that mistake too. It should be value. Whoops. My mistake. Slight caveat there too. Okay. A bit convoluted. Well, it's interesting this has such a high acceptance rate. It's kind of a challenging question, I would say. Let me look at some other test cases. I don't know, we could do like 1, 2, 3, 4, 5. Could do 5, 4, 3, 2, 1. We could do 1. We could do some random stuff. The numbers are between 1 and 1,000. Let's see what happens if I do this. Some of these test cases might not be quite correct. Not a valid binary search tree, case 6. Okay. All right, the left tree is smaller. This is the right tree. Left, right, and then, oh, I see. Let's do 6, 5, 6. Something like that. I think I need to make the trees larger to test this properly. Let's do like 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then permute this a bit so we can get like, I don't know, 15, 14, 18, 17, 16, 18, 17, 16, 15, 14, 13, 10, 11, 12, 13 here. Yeah, 9, 8, 7, I don't know. I don't know how to, I don't really know. It's a little confusing. Case 8. So this will be the oh, this can't be this has to be like 10 to be in the middle, and then left subtree has got to be the smaller values, and then the right subtree could be these larger values. And I think we got to put like, so here we have the right subtree, but then this is too large, so it's got to be like the left subtree, 18, 17, 16, 15, like this. I don't even know. Where's 1? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Where's 14? 14 needs to be here somewhere. 14. I don't know. I don't know about this one. Test cases. It's kind of hard to construct the test cases. Case 8. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, this maybe should be 19 then. 19, 18, 17, 16. Something like this. I don't know. I don't think these are great test cases. All right, so left subtree is here. Then there's a right subtree here. Then there's a right subtree 19 there. Then, oh, I see. The left subtree for 19 needs to start with this stuff. I don't know. Does that work? Left subtree, so root, right subtree, then there's another right subtree here, which has a right subtree there, which then has, oh, it can't have the left subtree there though. You need to do the whole left subtree first, you know, this one, and then you can do the right subtree. Something like this. It's quite a little complicated. I think I'm gonna just go for it. I don't know. It's probably wrong. It's kind of hard to go through all the tests. Oh, got it. All right. What? I mean, okay, take it. I mean, all right. Sure. Maybe I should have not try to do this iteratively. Maybe that's why it was so confusing. Why it took so long. Maybe when everyone else did this recursively, and I just was like, oh, I'll do it iteratively. All right, I'm going to submit this 5 times and then go on to the next thing. Not much to say about this. I didn't really prove it. I just kind of think it's correct. Use some reasoning, I guess. I don't really know how to explain it. 1, 2, 3, 4, 4, please, 4, 4, give me 4. All right. So capacity to ship packages within D days. Copy. We'll come back to that shortly. 1, 2, 3, 4, and we'll go for a 5th one. Yeah, that's not the fastest. Maybe there is a faster way. That's fine. Probably doing it using recursion of some kind is probably what folks did. But this is fine. This works. Simple, relatively simple idea. It's a little bit sophisticated. Basically saying that we're just going to push every value into a stack. So then whatever on the top of the stack is the last value we saw. We can compare our current value to the previous value and say, all right, if it's smaller, we just keep pushing to the left subtree. If it's larger, then we need to figure out which node we need to put this on to make it the right subtree. And it may have to pop some things in the stack going all the way up, even possibly going all the way up. And we're looking at the parent and grandparent, really comparing against the grandparent, but also updating the parent as we go. That's the basic idea. Pretty straightforward. Pretty straightforward. So let's go ahead and stop there. I'm gonna update the. If you like the video, give it a like and follow the stream. I'll restart the stream with a new title and keep going from there. So yeah, thank you for watching.